Also, today we're very happy to have Anu talk to us. He is an incoming assistant professor at Descriptive Computing at Georgia Tech, where he will lead the People, AI, and Robotics group. So it's got short for PAIR group. Also a senior researcher at NVIDIA Research, and is currently on leave from the Department of Computer Science at University of Toronto. And he's also a CFA chair position at Predictive Institute. Done his PhD in UC Berkeley, and after which he was a postdoc for AI Lab. His work built generalizable autonomy, which involves of representations and algorithms for reinforcement learning, control, and perception. He currently studies three aspects: learning, structured inductive biases in decision making, using data causal discovery, and transfer to real robots, all in the purview of embodied systems. So thanks for joining us today, Animesh. We're super excited to hear your talk.
Absolutely. Thanks a lot for inviting me, and thanks a lot for making time to be here. Okay, so let's get started. What I want to talk to you about today is I would like to say a bit more philosophical than just presenting the latest results from the latest papers. Hopefully it would be enjoyable. I would love for you guys to all ask questions as we go along. And of course, we will try to leave time or as much time for discussion after as well. In terms of what I want to talk to you about is what I like to call this idea of what are the foundations or the building blocks for autonomy. I started out my career in robotics, but these days I would argue that I work equal parts in perception, decision-making, and with physical robots. That includes methods in machine learning, computer vision, and robotics. And increasingly, we actually publish across these lines as well. Well, eventually the goal is to build a system that can work kind of out of the box. But we are far from it, I would argue. There is a lot of interesting new work that is coming out that will not be covered in this talk. However, if you guys want to talk about that, I would be more than happy to do this as well. So let's get started. Well, I would like to say, what do we want? We want robots, and when do we want them? Well, yesterday. Why is it not working? Because, well, generalization. Robots don't need to work, first of all, for one task. We want to do these things in many environments, many tasks. And more interestingly, it should work in different settings. Maybe my home, your home, my mom's home. Well, otherwise, it's not really a useful robot, is it? So, to a room full of vision scientists and robotic scientists, selling the problem is less exciting. It's really, we should be talking about how. So the problem is very simple. We want to understand the basic principles of reasoning and control so that we can do a large set of things with these systems. However, the problem is how. I argue that the how can be addressed with a two-step process. We need, one, a mechanism to specify the task, which is actually surprisingly very hard. Right? Think of how do you specify that a robot build a chair or cut onions for that matter? It requires a lot of careful thinking about how the task is specified, what the perception state is. And this input may come through the operation, language instruction, video instruction, a set of sequence of images. There are a variety of mechanisms to specify the task. So we need algorithms that can essentially what I would call perform task imitation in a specific setup. And then we need a phase two where we can generalize, in the sense we can take this idea or concept and we can generalize to various instances of this problem, whether it's building different chairs or cutting different onions in different shapes. Okay. Now these problems can be attempted with, I would argue, rather comically, but two very different paradigms. One can be more conventional robotics paradigm, where we have a perception, planning, and control pipeline, which are independent processes. These systems are built by experts, often for structured environments. This has served us very well, by the way. the other option can be we are trying to learn all of these components. And again, I think of this as a caricaturish example. People are, of course, slightly smarter than this. But it is indeed saying that we want to learn these processes, whether it's the perception, planning, or control, or perhaps all of it altogether. Now, neither of these things actually are sufficient, if you will, right? Well, experts are not always available, and there's always performance versus flexibility trade-off in building such solutions. On the contrary, at this point, adding data may not be computationally sustainable, even if you've had the data somehow, who has access? And finally, as we have seen with large pre-trained models, that somehow, even if you can train something like this, there is always this sort of out of distribution error problem that we seem to not be able to solve. So this is where I say I find a lot of inspiration in both philosophy and neuroscience, many of whom I argue are studying very similar questions as we are in, let's say, AI, vision, and robotics. Basically, how should learning happen? And one of the core recurring themes has been that from philosophy to psychology to machine learning and even deep learning, experts have agreed that particular kinds of inductive biases, or to be very specific, extra sources of information are needed to generalize beyond the dataset. This is very important because a lot of people think it's just add data and we'll be done. There's a lot of argumentation, both philosophical and technical, which says that you need extra information. What is this extra information? Basically, this extra information is what I call structure. Structure can be of different types. It can be domain knowledge, inductive bias in your architecture, symmetries, priors, all sorts of stuff. But you need something, right? We do use some structure actually. It's just that we don't always think of that as a structure. And then, of course, I'm not saying that we don't need data, but what kind of data do we need matters. Data itself can be online, offline, simulated, real, labeled, self-supervised, human in the loop, synthetic. So there is shades and tones and tints. There is nuances to this problem. Now, if I look at literature and vision and language, one could argue that ingredients of modern machine learning seem to be built on these ideas where there is some sort of large structured model. Usually there is some sort of structured bias, whether it's attention or convolution or something else, but it's not, let's say, simple. Often these models are over-parameterized. There are large data sets, many times IID, not always. And there is this idea of distributed deployment and compute. And this seems to be working kind of monotonically for vision and language. Language more so than everything else, actually. Just seems sort of increasing. And this slide might already feel dated because every 6 months, things seem to change. But importantly, what happens is if you go from passive offline decisions to online in-the-loop decisions, a lot of these assumptions break in the sense that if you look at robotics, the joke I have is, well, deep RL is not really very deep. The models are fairly small. Data sets are rarely IID and not even transferable across tasks. And because you don't have either the model or the data, well, what are you going to do with the compute to begin with? And one could even argue that this is a joke here that the kid figures out that you can solve the problem by just taking the lid off. Why bother doing all of this fancy stuff? Folks in neuroscience have argued here that the notion of intelligence exists to serve motion. Additional information or cognitive behavior such as sensory behavior, memory, cognitive functions are in a sense in the service of future motion. This is a very motion chauvinistic view of the world. And they have provided evidence that there are organisms in the environment which eat up their own brain once the need for motion goes away. Now, I'm not saying that this is always true, but it does appear that motion and interaction results in what we need to see, what we need to observe. In fact, this argument that the set of tasks defines what we do or how the world evolves is actually built both in nature and nurture. For instance, neuroscientists have provided experimental evidence that humans have the ability or specialized pathways to see scenes and faces. This evidence was already there for adults, but recently, Rebecca Sachs at MIT has shown that this separation, if you will, exists in very, very young babies already, even before they are able to actually see, in the sense that this exists up to, I think, 2 or 3 month old babies already, which is basically saying that they are built to see people. One could argue that the task of identifying and interacting with people is so necessary to humans for their survival that we have this morphological specialization in the architecture itself. And the specialization also occurs in the learning process itself. So this is yet another study where experimentalists have found that babies have the ability to learn different languages or learn different, let's say, individuals in different species. So for example, when you show a picture of monkeys to the baby, they are 3 individuals, but to an adult, they are all monkeys. This ability to distinguish individuals in a different species goes away as they grow up by, let's say, about a year in age or 2. This basically indicates that both nature and nurture kind of have this ability to specialize to the tasks we have at hand. And often those tasks are actually because of our need for interaction in the environment. This brings me back to the questions in robotics. Why was I talking about this? Basically, the reason why I'm talking about this is we as a community haven't figured out what such structures and specializations should be for embodied decision making. So today's talk is going to focus on that. We'll first try to talk about structure in vision and perception and decision making for robotics. Then I will talk about ideas of data, and if time permits, we can discuss discovery as well. So let's talk about structure first. What sort of problems should we be studying, and what kind of structure pops up? So within this space, I'm going to give you examples of structure in 3 different places for robotics. So let's get started with object-oriented representations first, where the questions are, first of all, what sort of mechanisms should we be using to represent objects? Then how to build models of these objects, and can we build more efficient modular models? So a question in robotics that often comes up is this idea of assembly. In the sense, essentially, it's picking 2 objects together. And this problem is very commonplace, whether it's something that is industrial or in an everyday sense when you're putting a pen in a socket, or a pen in a cap, or a plug in a socket. And this is a very geometric problem. It's not always semantic in a sense. And of course, a very extended version of this problem can be purely geometric, where you are trying to put together a broken vase, or heal broken bones, or put together broken sculpture. Or if you have, dinosaurs in natural history museums, you would argue that archaeologists don't find dinosaurs in that form. In fact, they find only a few bones and reconstruct everything else. So in a sense, we have this innate ability to figure out the whole from very few parts. So we started out trying to study something like that. So we said, okay, let's take a shape data set. We can create from every shape very different types of cuts. The cuts are not always planar, so they can basically be internally structured. And then we can also make this hard by making some of the objects rigid versus, let's say, hollow, so that the surfaces where you need to match are not always dense. So then we can start with this problem where you can take an object, which is now fractured into a shape pair. You can take point cloud representation of each of the fractured part. And the technical problem we are interested in is put this together into a shape that matches, let's say, a data set or the original shape in this. On the face of it, this problem is fairly simple. You are basically given two objects, both of two parts, which are both rigid. We need to predict a relative rotation and translation for each of these parts, such that when put together, they result in something. It is important to note that only the final result has semantics. The parts may not have any semantics at all. In this case, these are arbitrary fractured parts rather than, let's say, semantic parts of an object. Of course, the semantic parts are also a valid subset of these problems. So when you take this setup and you use something more classical, let's say iterative closest point, which is basically to align two point clouds together, we find that the results are rather disappointing. Mostly because usually these shape alignment or point cloud alignment methods were built to align two shapes so that they can overlap each other. So you take a bunny and you take a deformed bunny or scaled bunny, and then you put it together. But they were not built to put two parts together, which have a very small, let's say, interface. So a pen and a pen cap are two independent entities that need to be put together. And if there is a very small shared interface, because loss is only defined at the interface, these methods often fail very, very badly. So we started with a prediction problem. The prediction problem can be at least easily started with the pose estimation loss straight up. So you take each of these objects, you encode them as point clouds, and then a simple sort of not very deep transformer architecture is used to regress both rotation and translation. We found that was not actually sufficient. So we actually had to add structure here, or prior in this case. The prior comes from data set, where not every possible connection is reasonable. You can take two objects, let's say a phone and a pen, and if you connect them like this, it's not a meaningful connection. So that the final object should have, let's say, likelihood of being a real object. So this is just an adversarial loss. And then we also add a shape completion loss, which is basically saying that for every part, you should be able to complete the missing part of the shape. So you can actually impute what is missing in this sense. So adding both of these things was absolutely essential for the model to be able to predict interesting outputs. So in this case, we find that our model is able to predict reasonably correct part assemblies. In this particular case, this is only two-part assemblies. But the point was not to say that, oh, we are much better than baselines. But the point was, this was a problem that was not really a popular problem in vision. It is one of those problems that falls in the cracks between vision and robotics. So this was published at CVPR, and there were really not a lot of baselines to compare this with to begin with. And this is some qualitative results for a variety of different shapes. The important thing to note here is that neither are we specific to particular categories or particular shapes, because we are basically building this out of arbitrary point clouds that are fractured. So whether it's a cup or a plate or an arbitrary toy, all of them are fair game. But this does not stop the problem, right? We have done this pairwise. We were saying, why stop at pairs? So we took this idea and we said, okay, we can take a fracturing algorithm and fracture any shape into many, many parts rather than just two. And we did exactly that. So we took PartNet and Thingy10K, and then we used a pre-built sort of fracturing algorithm, and we fractured the same object in different parts, and every time you fracture it, it results in a different, let's say, set of objects. So we created a data set which we cheekily called Breaking Bad. And it's basically a reasonably large data set, or the largest of its own kind, for doing this sort of fracture assembly, geometric assembly. The problem is still the same. You have n parts now instead of two. You have to predict the right configuration that will result in a semantic object. And in this particular case, we found that even our model wasn't really working very well. That is why this is such an interesting open problem. It's so simple to state, but doesn't seem to be solved by any of the standard models. Mostly because if you have very small parts, doing shape completion becomes very hard. So for example, if I only show you the bottle cap, shape completion doesn't actually work with just the bottle cap because the space of possible shapes is still very large. Similarly, when you have many pieces, the configuration prediction is actually becomes a combinatorial problem again, which makes it very hard to predict the right final configuration. That is why, well, we joke around that this is a dataset paper rather than a methods paper. But nonetheless, what it shows is that the current methods are fairly poor, but this problem of being able to take parts and assemble them into semantic shapes is a geometric ability that people seem to innately have, but we don't have this yet in learned or algorithmic agents. So in this particular case, what we're learning really is that we need to learn object representations without assigning semantics to them to be able to understand the world. Semantics often comes after. So we need to have a geometric understanding of the world first up. Now, we want to go from representing objects to, well, building object-based models. In this particular case, this is something that we've been studying for a while. And the idea is here that we want to build predictive models. And I would like to start with this simple game, where the game is, I'm going to show you a video and you have to predict at least what the model might be. Let me give you the answer for a first example. This is one ball bouncing. The environment does not have damping or restitution, so the ball keeps bouncing. This is for you guys to decide. So if you looked carefully, I was actually just joking. This is just more balls in the same box with no damping. So the model is fairly easy to infer in this case. More interesting case is this one. Look carefully at the balls. They might change direction without actually hitting the walls. Feel free to write in your answers in the chat if you're not unmuted.
Can't figure out the blue ball.
Yeah. So I think interestingly, most people just come up with this answer that like, this is, I can observe the variables, which is 5 balls, but I don't know what the connections are. And let me tell you the answer. The answer is this. The connections are simple. I come up with an adjacency matrix where there are some connections are rigid, some connections are spring, some are string, and then sometimes there is no connection. And that is why, so for example, if there exists a string, the balls can sort of change direction depending on where they are, right? And now one could argue, oh, but I can learn this with the interaction network or a graph network. Turns out, no, we actually tried. It doesn't work because these systems assume that the underlying mechanisms are fixed. Only the number of variables is changing. But if I randomly change the underlying unobserved adjacency matrix, I can change the spring constant or I can remove the spring. So your observation space still remains the same, but the underlying mechanisms change arbitrarily from example to example. You need a mechanism to be able to generalize to new latent graphs. Each test case may be a different underlying graph itself, not just a known fixed dynamics. And then this is exactly what we can use in places where we don't even know variables. If I want to model, let's say, fabrics in a reduced model, I want to be able to model with the same system a shirt, a pantsuit, or maybe even, let's say, women's tops, which are asymmetric and may not have easy to identify, let's say, seam lengths. So this is exactly what we did. So we started out with this argument that we can start with some visual observations of an environment, of an object. First of all, we need to convert this to some state representation. So in this particular case, we made a choice for state representation to be key points. key points can be constructed out of unsupervised representation models. So you can discover salient key points through a reconstruction objective, frame-wise reconstruction objective. Using these key points as variables, we need to define a causal graph over key points. So in this case, that we define this to be a graph induction problem, and the graph can be, first of all, predict which edges exist, what are the edge types, and what are the edge parameters. And then using this graph, you have to predict the dynamics. The important thing to note here is that there is no intermediate loss. The only loss exists at prediction. So there's only prediction loss. There is no, let's say, supervision provided at the level of graph or edge parameters or that matter. And we then use the same model to learn a reduced order dynamics model for things where even having ground truth states is not obvious. So for example, a cloth can be modeled with a very high dimensional FEM system, but in this particular case, we show that modeling it with 8 key points is sufficient, and figuring out what edges exist allows us to model the dynamics of the cloth so that we can use it to predict, let's say, what interactions will result in what state. And importantly, the same model, not a different model with different weights for different objects. The same model also works for t-shirts. You can vary the t-shirt shape, let's say half sleeves, full sleeves, or change, let's say, some of the textures or stiffness of the object. And same thing also works for pants. So the point is here, using the right underlying representation, and in this particular case, the causal inductive bias, enables us to build more general models for object dynamics. So that was point 2. Now, one more thing that we would like to generalize to is, as we said, in this particular case, we were using fixed unsupervised key points, but often key points may not be sufficient representations of the environment. Sometimes you might need more than just pixel level locations in XY, or maybe even XYZ to describe scenes. So in that case, we have tried to now generalize this idea beyond key points, and still trying to keep the level of supervision the same. So we don't want to provide any intermediate supervision. The only supervision should, in principle, come from prediction. So in this case, we resort to this idea of slot attention. For those of you who may not know about slots, they were recently introduced, in the sense, about 3 years ago. And the idea is fairly simple, that you can take an image or take scene and decompose that or disentangle that into a set of, let's say, components. The components in this particular case can be object-oriented. So you can have a background and object-oriented setup where each object composes of a different component, and then you can compose them or with a decoder into a full scene. And we take the same idea where we can say the slot encoder allows us to go from images to slots. But this time around, instead of using a very simple RNN, we use a dynamics model, which is a prediction model in the transformer architecture, and doing prediction in the slot space, in the latent space, rather than in the image space. And again, we can do some rollouts. The loss comes from reconstruction directly. Notice that the fact that the transformer is an attention style architecture, in principle, it gives you an interpretation of causality, where at every given time step, t+1, the model can be attending to not just the last time step, because we are not assuming complete Markovian information, to any of the previous steps, and ideally, let's say, a sparse attention model, so that you know explicit what times matter. So first question in this setup was, obviously, does this model actually do prediction correctly? So we compare it to a variety of prediction models that are currently popular for video prediction. And we find that, of course, the results numerically were similar in the sense that we get similar results. But the most important thing we are able to do with object-oriented models is to keep semantic sanity, in the sense that objects don't disappear midway into Gaussian blurs, or objects don't change their properties. So for example, if you notice in the VQ former, over time, objects change color. The cube becomes from think in the original case, it's yellow, but the cube becomes green, and then it changes color over time. In other cases, for example, Savi, the objects essentially just disappear into a Gaussian blur. So in a sense that we can predict and preserve semantics, this is the most important part that I think we were able to achieve with the object-oriented dynamics. Now you can use this model to do interesting Q&A. First question was visual question answering. Can we do interesting questions? In this particular case, the question is, you have to predict the cube and the blue sphere collide. What will happen next? And in this case, the answer is kind of binary. But the important thing is you have to predict this event through multiple collisions. So we provide few time steps upfront, and we make it predict the events in the future to be able to answer this question. And importantly, we see numerically that based on all of the other baselines in this data set for VQA, our method is kind of competitive almost always. The method that we are using is actually in Magenta in this case, but most important takeaway is we are able to achieve similar level of performance with an unsupervised method, while all of the other methods are using some sort of prior, in the sense they are using object detectors that are pre-trained or explicit sort of symbolic systems to be able to predict these systems. So being able to achieve similar level of predictive performance, even though the model is not explicitly built for this particular task, was a win according to me. And to carry this forward, and this is exactly what we show qualitatively here, that if you look at the bottom figure, will the blue cube and the purple cube collide next requires you to reason through two collisions, where the purple cube first collides with the cyan cylinder, then the cyan cylinder collides with the golden ball, and then the change of direction results in blue cube and purple cube colliding. This sort of semantic decisions require long-term consistency in prediction, which many of the models don't always have. Now, this was still simple, so we said, can we use this model for actually making decisions? So we looked at a game, which is called a Physian dataset. In this case, the game is very simple. You have to decide where to place the red ball, such that at the end of the episode, the blue object and then the green object need to eventually touch. And the interesting thing is, every environment can be a different configuration, different scene, different setup. So you really need to learn underlying principles of physics in this setup. So in this case, we again run a slot former model, and we find that first of all, the model discovers the right set of components in the environment. For example, all the separate balls, all of the sticks that decide the physics or that have effect on the physics. And then we do rollouts, and in this case, we find if not the best, we are nearly the best again in this setup. The most important takeaway here was the model was not built for any of these tasks specifically, whether the decision-making task or the VQA task. We built the model purely for prediction tasks. The fact that the model has the right structure and an underlying inductive bias allows us to solve multiple tasks in a more generic setting. So far, I've only talked about this idea that you can have structure in perception.
I think a question from Ishan.
Yes.
Go ahead.
Hi, Professor. Yeah, I'm curious with some of these questions, like with the environment that you showed, the Cater kind of environment. The multi-view supervision is quite natural to the data set. So I was wondering if you ever tested with questions that included like occlusions or something, if the prediction quality degraded with some sort of occlusion in your data set, and whether like having a nerve style object-centric supervision where you perhaps learn like a representation like slots, but maybe nerve supervised or multi-view supervised will help expand
the
the
underlying
method.
representation is capturing something in 3D rather than view dependent 2D. Am I correct?
Exactly. So your input is still 2D, but you
Yes,
learn some object-centric representation that is decoded in a different viewpoint, and you use some nerve sort of supervision as well.
So we did not,
that
for this particular paper, we did not. This is something that's actually very interesting. With multi-view, if you have camera poses, then there is some sort of reference frame to decode this into. If you don't have explicit camera poses, then you also have to solve for some sort of correspondence problem. That seems to be slightly more open-ended. When you do have camera poses and let's say a global coordinate frame to make predictions in that case, I think this might be interesting to do predictions in for multi-object collisions in 3D would be. I think the problem would still be slightly more challenging because then the data set would need to be strictly much larger than what these data sets are because of the need to be able to predict from arbitrary viewpoints.
Gotcha.
But I think this is a completely valid thing to try. We have not tried it, so I don't know what will happen aside from like increasing the data set size. But I think you will need to change the architecture to capture let's say, the correct coordinate frames in which you're doing predictions. And then the other question would be, are you decoding independent arbitrary frames? So for example, if you are doing predictions in 3D in the slots, then is the decoder view dependent? Because that would be an independent problem because essentially you're asking it to render from arbitrary scenes or arbitrary viewpoints. Right. That may be a hard problem in and of itself. If you have a fixed viewpoint decoder, then this could be attempted. I will show you an example.
Gotcha. Thank you.
Thanks a lot. So far, I've only talked about perception, but it appears that decision-making, RL, seems to be equally rich or in terms of needing structure. So we talked about this idea that you can have different kinds of structure in decision in perception or even language, for example, whether it's independence, locality, sequentiality, tension, and then how you train the model itself can also induce structure, whether you're using contrastive methods or some sort of attention mechanisms. But when we think of reinforcement learning, just as a very simple primer in reinforcement learning, you can really think of this as a mechanism where it takes in some sort of input. The input is passed to some agent. The agent in robotics can be, let's say, an NLP that outputs some action. In the case of robotics, let's say it's a joint level torque, and then that's passed to some environment. And then this loop is updated, or the agent is updated with some sort of iterative update rule, let's say Q learning, but it can be other things as well. And this pipeline has given us a lot of interesting things in recent times, particularly in robotics, where we are now able to do vision-based control. However, there is one technical problem. Almost always, these tasks are very specific, and they almost don't generalize to anything but that setup. So for example, what I do in my lab may not work in your lab at Columbia. The algorithms somehow are lacking either shareable structure or shareable weights, which either are learning things fast in the sense they can learn new tasks fast, or learning many tasks in a general purpose setting. This is something that is very open. And I argue the question really is, we are missing a lot of structured bias in the decision-making process. And to understand what we are missing, we really need to go slightly inside the box, beyond the usual RL loop. So how does it work? To set up a realistic problem, I will have an observation, let's say images or some other demonstrations. I will pass this into a perception block. The perception block will pass this into an agent. An agent will output this to an action decoder. Just to give you a sense, the perception block can be any sort of processing or pre-processing you are going to do on the input. On the contrary, the action decoder would be something like your policy is outputting 10 Hertz action, and you want to convert that into a 300 Hertz closed loop control. Or maybe your policy is outputting end effector actions, you need to convert that into joint cases. And within the agent, you will also have these two other objects, which is transition model and a value function. Depending on what regime you are in, whether it's learning or planning, you might use these models differently. Now the question is, where is this structure? What are the insights that we have? I argue, well, there are insights galore everywhere. Let's think about how we solve this problem. One of the methods of solving this problem is called off-policy RL. For folks who do not know RL or are new to it, don't worry about this. The concept is very simple. You collect some data with some rollout. With this rolled out data, you do an update on what is called a value function or a utility function. You are basically fitting some sort of utility function based on your data. Given the latest update of the utility function, you can back out a new policy. It can be greedy. And then you continue the loop until you're happy. Now, let's look at the first problem, which is the update step. We are using function approximation to solve for this problem of Q function or value function. But we have always assumed, almost all the papers we have seen, that this is a very simple NLP. But we are not really questioning why. So the first thing to be asking the question here is, why does it have to be NLP? Different architecture such as ResNet could be helpful. That is exactly what we tried. We allowed ResNet architecture, a 4-layer ResNet architecture, instead of a standard NLP architecture to do function approximation. And to our surprise, almost all of the results in all of the benchmarks just improved. This was literally a few lines of change in code, but we were able to achieve a very high performance bump in many, many benchmarks. So we were not even sure how to write a paper about this. What we were able to explain is the sharing of information across layers allows a better inductive bias for the value function. But what this even more so says that the debate on what should the architecture be is far from settled. The other question is, we have been using this update equation essentially as biblical. In the sense, this has to be the update equation. But why so? Why is the utility function defined as such? It is not necessarily always the correct information. So let me give you a very simple example. You guys are college students. If you take an exam, do you always approach the exam with the same order? Even if, let's say, I say this is a take-home exam versus you have 15 minutes to finish the exam. One would argue that your order of attempting questions might actually be different. If you have infinite amount of time, which is the take-home version, you might attempt questions one by one because you're not worried about time. You really are asking for best solution. On the contrary, if you only have 15 minutes, you'll probably optimize for bang for buck, solve the easiest things first. But this model of utility function is only saying that the only type of solution we are interested in is infinite time horizon, infinite horizon. So we actually changed that. We had a paper last year where we showed that having a different utility function, which is time aware or horizon aware, can be much more useful. We can represent, first of all, multimodal policies, multi-goal policies that are horizon aware. And you can even think of this as a mechanism of a single variable tuning. So H can be used as H can be interpreted as a horizon, but also interpreted as a safety mechanism. So for example, if H is very low, then you can say, I'm very risky and I'm happy to come up with very risky solutions, but time is very low. On the other hand, if H is near infinity, I can say that I'm very conservative and I'm happy to be safe, but I don't want I don't want to sort of fail in the pursuit of a solution. So the point here is that we can rethink the process itself to come up with better solutions. Now, I showed you this model. This idea of structure also exists in transition models. Transition models are often trained with very simple MLPs to fit a data set. But instead of using MLPs to fit data sets, we can use object-centric models. And not only object-centric models, but also what we would argue, hierarchical object-centric models, where we are able to predict which objects to move and which directions to move them in, which allows us to make both discrete and continuous decisions. This is something that is often very hard to do in generic trajectory optimization because you have to make discrete and continuous decisions, and posing that as an optimization problem can be very hard. So learning a model which can capture both discrete and continuous variables allows you to do sampling-based motion planning with a learned motion model. The same thing can also be said when you're learning these dynamics models. You should not be taking MLE objective as the only objective you should operate with. We have found that the objective of learning the model should be task aware itself. When you're driving to work, you don't care about the pattern of the clouds in the sky. This is something that is irrelevant to the objective at hand, which is driving. So the model should be task relevant. So we showed that if you add a lot of distractor dimensions, then simple MLE-based model fitting approach fails very poorly, does very poorly. On the contrary, a system which can identify what we call vagrant, what are the right dimensions that we should care about, that are task relevant, enables us to learn a value-aware model or a task-aware model. So this is basically saying even learning the transition model is not as simple as we might be posing it. We have also shown that representation learning matters. In most vision-based robotic tasks, often one could argue that majority of the weights in the model lie in purely the visual representation itself. In our case, we found that our whole model was about 600,000 parameters, of which about 585,000 parameters were just in the perception stack. The policy was very simple. It turns out that if you train this correctly, you can actually do reinforcement learning directly on the real robot without having ever simulated in the pipeline. In this case, we showed that you can learn the representation, or multimodal representation of vision and touch that allows you to generalize to different shapes of peg at test time. So you can learn a new policy for a different peg much faster after the fact. Similarly, decoders also matter. In this particular case, we are showing that you can learn policy using a visual input. If you choose the right action space, then you can actually generalize to even a real robot from a purely simulation trained policy without any, let's say, robustification through domain randomization. Just the choice of action space matters. In this particular case, the choice of action space is what is called variable impedance end effector control, which is basically saying that if the robot is only going to interact with the world through the end effector, then I should not be thinking in terms of joint space. I should be thinking in terms of forces on the end effector. And the ability to do this allows us to actually do more. The same idea that you can have a reduced order control allows us to attempt tasks in sim2real for legged systems as well. The same idea works there as well. And in these cases, we were specifying the task space because we had information about the environment. But you can learn these things as well. So in this case, we show that if you have some data, you can learn a decoder, and the policy is operating in the reduced order space, low dimensional label space. And in doing so, we then actually ask humans to do teleoperation in reduced learned latent space. So what we are doing is a robot is doing, let's say, full 7-DOP command of pick and place, but the user is controlling this now with a 2-DOP input. And we found that a learned space was much faster and enabled users to achieve tasks through teleoperation 5 times better. So again, that the choice of structure in RL matters a lot. This structure exists at different levels, whether it's data augmentation, model architecture, the update function itself, or state and output encoders. But if there's one thing you take away from this, I hope it should be we are leaving a lot on the table. So far, I've talked about low-level skills. So for example, whether it was grasping, picking, wiping, and so on. But a lot of interesting things we want to do in real robotics are more than just first order skills, in the sense that we are not just doing picking and placement, but we need to do a lot more. And one could argue that we learn low-level skills through trial and error, but we learn complex tasks through imitation. Again, it has been argued a lot that humans transmit culture through imitation. If you were to try to make eggs, or I don't know, your favorite chicken tikka masala, if you were to be doing that purely through trial and error, you would literally run out of chickens in the world before you figure out what is a good recipe. On the contrary, cultural knowledge or tribal knowledge is handed over from generation to generation. And the same things could be argued for a lot of complex skills. Like, you were not born evolutionary to be using computers, but you still are able to use computers or drive cars, even though these are not naturally occurring objects. So now the question really was, how do we go from this to imitation? So first question we should be asking is, what to imitate? If there is some sort of task specification, a first order agent might be doing what I call imitative babbling, in the sense that the actions look similar as per the demonstration, but really we are not making progress toward the real task, which in this case is actually sweeping the leaves. As you grow up, you figure out that, well, figuring out what are the sequence of skills is important, and then skill sequencing with dexterity gives you a lot of advantage in completing the task. And then when you grow up a bit more, you actually understand the assignment. So in this case, the assignment is, well, cleaning up. It doesn't matter what actions you use. So you have understanding of semantic purpose, while the action space that you use might be very different. This is exactly what a lot of my recent work is, which is saying that we can separate the what and the how of the problem. So the what can basically be a causal generative model, let's say, to learn to predict the effect of an action. And then we can figure out how to solve this problem. So first of all, we need to understand, what does it mean to do something or apply an action to a scene? For example, open a door, open a jar, or open an object that I don't have an identity for. And then we can actually do something with this. So for example, we can apply actions and we can do planning with the system. This idea is called prospection or mental simulation, where you're first thinking about what to do in the environment, and you're not really thinking how you will achieve this. You're thinking of, like, if I do something in the environment, how would the environment change? And then you're basically figuring out, now that I know what the change needs to be, I will figure out what the actual actions or the joints and the forces need to be. And this is exactly can be used. I can take this idea of generative models and then pass this generated image or generated sequence to a goal condition controller that can, in principle, solve online for this task. So if I want to open an oven, I need to first understand what is the concept of opening the oven. This is actually solving two technical problems. One, with a causal generative model, I can learn large-scale pre-trained models of knowledge about the world, which are completely agent agnostic, which is very much in line with, let's say, recent results in the community. And two, for the robotics or the RL part, usually one of the hardest part is specifying the task or specifying the reward function. Where does the reward function to open an oven come from, actually? And this allows us to solve both of those problems with a single frame. So let me show you how we did this, I think in the 5 minutes we have. So the first problem is indeed the ability to do semantic action conditional prediction. In this case, the data set that we started out with was the same cleverer data set. And I showed you this idea of slot-based predictions. We used a similar architecture. I think in the interest of time, I might skip through the details of the architecture, but show you the results. In this case, we start with input first frame, and this time around, the prediction is actually conditional on language input. In this case, language was simplified tokens. And of course, you can compare it with ground truth. We were able to show that this system works not only for simulated data sets, but also realistic setups. But the more important part is now we can start with the same start state, but provide completely different, unseen, let's say, sequence of actions or counterfactual instruction, and still be able to predict something. And importantly, as before, The question is to maintain semantic consistency. So for example, if I move, let's say the purple plate and put it in the small blue bowl, there should still be only one purple container rather than replicating the purple container, or it should still be as crisp as possible. And we also found that we are able to generalize this because of the fact that we have a system which is modular in the sense. So we can keep attributes out of the data set. So for example, all red cubes are removed, but at test time, we can still ask for predictions of that kind of object. Of course, since this work was done last year, a number of interesting results have come out in the space of text to image and even text to video. However, what we have found is that these models are very good with nouns and adjectives. Let's say a person with a black shirt or a photo of an open box, and less accurate with verbs and adverbs. Can you open the fridge, or can you drink water, kind of things. I'm hoping this will change soon as well. So given a mechanism to generate what I want the change in the world to be, I can actually go from that to policy. So what that problem is, I have some sort of object-centric planner, which takes in some input. The input is now passed into the system, which predicts what the state of the world should be. And then now I want to find a dynamically feasible, which would be a subset of this planner's setup such that I can actually execute this task. So what I'm showing you here is basically a system that can open arbitrary drawers without having any underlying 3D model, with only onboard sensing. And in this case, we're not even doing learning. This is classical control in this case, and we are only keeping track of some key points on the handles, which are detected automatically as well. And because this is a system which is basically using a generative model to predict what the sequence of, let's say, handle poses will be if this object is open, then you can go from that to, well, generating a system to do this. And of course, I do want to say, because we have this connected with more robust systems, I don't have to learn separately if there's an obstacle in the environment or not. So you can put this out on the real world and actually expect robust performance. So we talked about a variety of things today, and I think I want to bring this back. We might not have a lot of time beyond this, so I do want to bring this back. We talked about structure. I gave you examples that structure exists in the right perceptual representations. I also gave you examples on how we might think about structure for decision making when you're doing RL in the loop and you are learning representations for interaction. And finally, how one might approach the problem of large-scale, long-term decision making through the combination of generative models combined with goal condition planners. Because we are at the end of our times, I will not be able to show you much more, but I'd like to bring this to a close here, where if there's one thing that you take away from today's talk, please let it be this: to build practical systems for decision making, which require both perception and control architectures, we will need to rely on both structure and data. Just building larger data sets may not be the solution. The question of what that structure will be is not necessarily answered. It is an open-ended question. There are a lot of interesting characteristics. Sometimes these characteristics may be problem dependent, and there may not be a single universal solution for that structure. However, one thing appears to be certain, that some sort of prior information would be needed. And building that prior information gives us a lot of interesting questions as upcoming researchers in this field. So with that, I would like to thank all of you for inviting me. And again, I am very privileged to be speaking to you about all of the recent work that you've done. A lot of the work that I presented today is indeed not just my alone. A lot of collaborators and colleagues were involved, so it's thanks to them that I'm here. And thank you all. I'm happy for you to take any questions or to talk about other things as well. Thanks a lot.
Yeah. Thanks, Animesh. This was great. In the interest of time, we'll directly move to, and then if people have questions, they'll probably ask it. And usually pick one question.
Oh, if anyone has a question.
If anyone has a question, unmute yourself. Take maybe one. Anyone more?
Amish, I was curious about the slot attention. Guys going that spreads throughout the work. Is that just an architecture inductive bias you put in, or is there software we have to put on top of that to get that disentanglement out?
So, if I understand the question, you're arguing, is it just the architectural bias, or is there something special about that?
Well, I was seeing kind of practically. If I wanted to go use slot attention mechanism, my own work. Is it straightforward to just put that in the architecture and train it end to end, or is there more to it in terms of like a regulation you have to put on, right? You know, I'm just curious.
There are nuances. Yes, there are nuances. I should be clear. I think some of it was not clear. So slot attention can be done in different ways. So, for example, in this particular work, we train the slot encoder first, and then the transformer prediction later. There are some empirical challenges because when you are doing prediction and the slot encoder is completely unsupervised, how do you ensure that the tracks are correct? So, for example, if in time step T1, I have slots, let's say 3, 1, 2, and 3. In time step T2, it's not necessary that they are in the same order. So that is one technical problem. In an unsupervised setting, how do I ensure that red cube always falls in slot 1 throughout time? Right. So this is something that comes up in tracking as well. So that was one problem that we seem to have solved with. So we had to tinker with the right, let's say, noise and bias in the transformer architecture to ensure that the slot model ended up learning the same assignments across all times. Now, I think very recently, unpublished result, but will be out soon. We are now able to train the slot model with the encoder being slots, but the decoder being diffusion. And then you can train the whole thing end to end. And we have found that with a diffusion decoder, you can get much more crisper output in terms of reconstruction or, let's say, textures. The temporal prediction still is a transformer though. So there's a lot of what I would call empirical tribal knowledge that is in the GitHub rather than on paper. But to answer your question at this point, can I just go ahead and use it? I would encourage you to definitely try it with a caveat that the idea is actually very promising, object-oriented representation. However, empirically, slot attention models are limited to reasonably synthetic data sets. They have not been applied to what I would call in the wild data sets, and that's something that I accept. But I still am willing to push on this as a thing that we will make it work. That said, now what is more interesting is the whole idea of slots was to be able to disentangle basically underlying systems or field systems. Now, is the disentanglement always object-oriented? That part is not something I'm clear with. In the sense, if you look at these slot attention models, we are able to go from images to objects. But who is to say that the disentanglement is object-oriented? Why not attribute level? So, for example, why do I not have all circles and all cylinders in one slot, and then color is one attribute, and then I can still mix and match to convert into a scene? But that is a different kind of disentanglement that we don't need to observe, at least emerge. Now, one could argue in image to or text to image models, let's say any of the text to image models, this sort of disentanglement exists. It could be because they are kind of let's say weakly supervised because the tokens exist. In our case, we are only using images, so it's a harder problem. So maybe we need to revisit the problem with some tokenization or weak supervision. But that seems to be an open-ended problem. Overall, I think the thing is, I don't believe even if image or text-to-image models exist, they solve all the problems, because a lot of representations that we are interested in are context specific. So there is a very interesting problem I'm interested in, which is I think of this as evolving memory kind of thing. If I fix the operating memory of an agent, so let's say the number of slots is fixed. If I'm a car on the road, will I discover that the cafe on the side of the road has a table and a cup? And my argument is no. There is nothing in my task space that requires me to think about the cup. On the contrary, if I'm a humanoid robot, then the handle and the cup matter. So what goes in the slot actually matters dependent on what the agent is. That's insight one. Insight number two is it also depends on what task you're doing right now. So for example, if the agent is running, then perhaps it doesn't need to worry about the minutiae. So the car is just a one big blob of obstacle. But when the agent is trying to get in the car, then suddenly the car has wheels and a door, and the door has a handle. So the concept of objectness is actually not a temporally fixed, let's say, representation. It changes across time. And that would depend on the attention over task itself. I don't know of perception models that can do it right now. That is why we started working on slots. But that would be an interesting thing to emerge in a sense.
Yeah. Thank you. Yeah.
So, all right, let's thank her and move to one-on-one.
Thank you very much, Purva. And thank you everyone for making the time. And thanks a lot again for inviting me.